Okay, in this presentation we're going to look at information theory, and what I'm going to do is calculate entropy. Okay, measures information of or entropy, so it's a measure. So the Hartley symbol heart, also called a ban or a dit, I'm not really used to saying those. I usually call them Hartleys. Dit is short for decimal digit. Is a logarithmic unit which measures information or entropy based on base 10 algorithms or powers of 10. Usually I would work with bits, and that would be base 2, but this is just for the sake of variety, varying things. So just as a quick remark, one heart or one ban should correspond to 3.322 bits. Okay, so I'm going to do out this example down below, and I'll quickly compare it to the binary approach to it, the base 2 approach to it. Now, just slightly adjusting another thing here. This is our entropy formula, but rather than the minus probability times log to the probability, I've just expressed it in this alternative format here. Mathematically, this is exactly equivalent to what I would usually use, but here, just to sort of shake things up a little bit, I would actually use this approach here. So we have minus the probability times log to the base 10 of 1 over the probability. This actually also applies with the binary approach here, but again, I'll just sort of be consistent the whole way through this video, and in this case we will use log to the base 10. Okay, so I have a 4 symbol alphabet here, A, B, C, and D, and here I have the probabilities of each of those symbols, 0.5, 0.25, and 0.125 respectively for C and D. So when I calculate 1 over the probability of each, or divide 1 by each respective probability, I end up with 2, which is 1 divided by 0.5. 1 divided by 0.25 gives us 4. 1 divided by 0.125 gives us 8, and 8 there. Okay. So my next step is to calculate the logarithms of those. Now I have it to 5 decimal places here. I don't really need to do that. 0.3103, that's for A, which is 0.5, which is 1 over the probability, is 2. So the log to the base 10 of 2 is essentially 0.301. 0.602 for 4, or B, sorry. For C, which is 1 over probability, has 1 over the probability of 8, is 0.90309, and then likewise that's the same for D. So we multiply the probabilities by those logarithm values, okay, and we get 0.15051, 0.15051, which is the same again, it's 0.25 times 0.60206. C, we have 0.125 times 0.90309. That gives us 0.11288, and again that is also the same value for D. Okay, so when we add all of those up, we get 0.5268 Hartleys. Okay, now, so I'm just going to follow up with that very quickly. I'm just going to sort of show this example here. Here I'm actually using bits base 2 and minus p times log of p. Okay, so this is for a fair coin, which is a 2-character message source. Okay, heads or tails, and when they're equally probable, we have the entropy equals minus a half, which is 0.5, okay, times log to the base 2 of a half, and both characters have the same probabilities, so it's just double it in both cases. So we get 1/2 plus 1/2, that's 1 bit, okay. And when we do that for a biased coin, where the probabilities are 0.75 and 0.25, the calculations work the same way, and we end up with 0.81. Okay, now just to repeat the Hartley example that we had used previously, we use the same approach here. A is a half, B is a quarter, C and D are 1/8. So we have minus a half log to the base 2 of a half, minus a quarter times log to the base 2 of a quarter, minus 1/8 times log to the base 2 of 1/8, and again minus 1/8 log to the base 2 of 1/8. What you could do actually in these repeated symbols, actually, just as long as you're sure, remember what you're doing, is you can just collate them like that or compress them into one term. Okay? Anyway, when we work it all out, we get minus a half times minus 1 plus a quarter times minus 2 plus minus 2/8 times minus 3, and that adds up to be 1.75. And if you check that on your calculators, that does work out to be 0.268 by 3.322. Okay, so that does convert from Hartleys to bits. Okay, that's it.